can talk about this Poisson boundary of monoidal categories. And the last time I did this more historical background and the more overall motivation, so motivation from subfactor theory and quantum groups. But I didn't really define anything, so that's what I want to do today. So give definitions of these ingredients. And the next time on Monday next week, it will be more on the proofs using these operator algebra technique like entropy and Jensen's inequality and all these. So, but today it's mainly about the definitions. The first, of course, the most important thing is the monoidal category or tensor category after Longo and Roberts. I mean, the dimension theory for C-star tensor categories extending the theory of index for subfactors and quantum dimension of quantum groups. So first of all, the most fundamental notion is that of C-star category. So it's a basically the usual category, but also all the morphism set have this C-star structure, so norm and star structure. So C-star category, D is, first of all, a category, so you have objects and morphisms. So but then, so the morphisms are vector spaces over complex numbers. So that's called C-linear category. So I write the morphism sets like this. So X and Y are, so they are the objects in, in this category D. And then when I write DXY, that's morphism set. And first of all, I assume that this is a complex vector space. And then, so these vector spaces have C-star structure. That means there is a Banach norm. Most of the time, the most interesting examples are where these morphism sets are finite dimensional. So there isn't much issue of completeness, but still you want the C-star norm. So norm. And most importantly, there is an involution like in the C-star algebra. So this involution has to be conjugate linear. So the scalar can pop out as a conjugate number. And also, as in C-star algebra, so it's anti-multiplicative. So the order of product changes. Star structure. Maybe I'd better split up. So lambda T star is lambda bar T star, and ST star is T star S star, and satisfying the C star identity. So T star T. So the norm of this has to be square norm of T, and also its isometry, or so you get this identity also. So this is the C-star condition. And then once you have these structures, for example, the endomorphism ring of any object, so when X and Y are equal, so that's a C-star algebra because you have Banach norm and star structure satisfying C-star identity. So and it's going to be Abishevre. So when I write just dx, that means dxx. So the endomorphism ring. So these are C-star algebras. And moreover, the general morphism sets like this Hilbert modules over these C-star algebras. That means you have an inner product on this space, but the value takes place in this C-star algebra. So the inner product of S and T in this algebra, and that's linear in T, anti-linear in S. So there's only one way to make sense of it. So it takes S star and then compose with T. That means S star is a morphism from Y to X. So if you take this composition, it's something living here. And then, so you can verify all the standard axioms of these Hilbert dx modules. So this is completely positive and also faithful. Okay. So that's the really general thing. And for example, the category Hilbert spaces or module, bimodule categories of subfactor satisfy these conditions. Because basically they are already realized by Hilbert spaces. So you can just take the usual star operation of the operators, and of course they satisfy this C-star condition. Okay, so that's the most fundamental thing. And as I told you, so I want to, most of the time, I'm interested in the case when these morphisms are finite dimensional. And that's called the semi-simple case. Because in that case, these C-star algebras are just finite dimensional algebras. So you can chop up, you can decompose all the objects into simple sub-objects by just taking minimal projections in this C-star algebra. So. So you can do reducible decomposition. Irreducible. Okay, so that's that general framework. And then, yeah?
Are you saying there is a consequence?
Yeah, so.
Why should the range of Penrose?
Yes, oh yeah, that's very good question. So, but that part is rather, yeah, so maybe it's a bit, so after taking, yes, yeah, that's very good point. After taking what's called idempotent completion. So there's a standard way to do this. So yeah, so in general, it's not guaranteed that this original category D itself has sub-object, but still, so you can regard these minimal projections as the sort of new objects, and then, so there is a very standard way to extend. So after taking sub-object. Completion. But we always assume this, so all the idempotent represent some sub-object. Okay, then, so the tensor category is a bit more, there's a bit more structure. Namely, you can take tensor product of things. A C-star tensor category, I'll call it C, is first of all a C-star category like this, and then you can take tensor product. That's bifunctor. So the two things come from this category, and then take the tensor product, you again in the same category. So I write it like this. And then bifunctor means this operation is natural both in x and y. And then, so there should be a tensor unit, multiplicative unit for this operation. So I write it like the multiplicative unit, 1. So, and then, so of course, saying that this is a multiplicative unit means 1 times x or x times 1 are naturally isomorphic to x. And also, when you take tensor product of 3 things, you want to be able to say that the result is essentially the same. So, and because we already have the star structure, so all these comparisons should be unitary. So U star U and U star are identity, unitary transformations. For example, 1 times x is isomorphic to x, and also x times 1. And so I'm keeping notation for the comparison of associativity comparison. So the comparison of 3 things. Oops. And then, so of course, these need to satisfy the compatibility relation. I wouldn't write all the relations, but so this is really standard. So the, for example, when you take when one of these is 1, then you want to say that this is essentially the same thing up to these isomorphisms. And also, for example, the product of 4 things should produce the same thing. So from x times y times z times w. And there are 2 different ways to go to the other, so the other extreme, z times w times y times x. So, so you can, for example, first, do it from outside, then. Or do it from inside, and then so. And then go like this, and these 2 should commute. And this looks sort of obvious, but then when you start to expand the definition, this condition actually looks like 3 cocycle condition on a group. And also the condition of compatibility of phi and these unit morphisms are the normalization of the cocycles. So usually you don't care that much about this associator phi, but when you start classifying these categories, then so this 3 cocycle condition is really important. function. So let's say gamma is a discrete group, and then so you look at the 3-point function on gamma into U1. And then, so this corresponds to phi by z w phi x y 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 z, this one. So well, so these lowercase letters and uppercase letters play the same role. And then, so this commutativity can be represented in this way. So, yeah, so this is pretty something to keep in your mind. Okay. Then, of course, another fundamental notion is the notion of functor. So when you have these categories, you want to compare them. For example, compare against the category Hilbert spaces. So let's say you have two C-star tensor categories in this way. Then tensor functor it's of course it should be a functor from C to D, but then it's a bit misleading if you just say so, because we also need to take care of these distinguished object tensor unit, and also the comparison of tensor product in these two categories. So it's actually triple. F0, F2. But when you're sloppy, you also just write this as F. So F is a functor. But then, because they are involution, so you want to respect that. And F0 compares 1 in the target D and the image of 1 in C. And F2 compares the tensor product in these two categories. So and again, so this should satisfy the compatibility condition with the associators and unit morphisms in the C and D. But that's, you can work it out, I mean, looking at the definitions. Okay, I didn't miss things too much. Yeah, but the important thing is quantum group is really characterized by such data, such categorical data. So that's a Tanaka-Klein duality. So to think about a compact quantum group is the same thing as talking about such pair where for the D being Hilbert space category. So so to think about compact quantum group G is the same thing as category of, think about the abstract category of unitary representations, which is a C-star tensor category, and then tensor functor. So which forgets about the information of representation and just gives underlying Hilbert space. So this is C-star tensor functor in that way. And so out of this pair, you can recover G. So this is the Tanaka-Klein duality. And then, so for the case of subfactor, whether you can recover the original subfactor out of these categorical things is the content of Popper's classification. So I don't go too much today. And another important thing is the dimension theory. So for these subfactors and content groups, you don't just have these C-star tensor categories, but all these things have contra-gradient things or conjugate objects. So any object have a conjugate. So we want to formalize it. C is a C-star tensor. And X is some object. And then, so we say another object is a conjugate of X, or dual of X. If you can find the duality morphisms, what does it mean to for a representation like this to be a dual of one other thing? So that's when you have trivial representation inside the tensor product and in a nice way. So embedding trivial representations inside tensor products, that's the first requirement, of course. But then, in general, y times x and x times y aren't guaranteed to be equal, so you want to have both. And then, so you also need to say that y is exactly dual of x, not just something containing it. So, for example, if you look at, oh, sorry, that should be x. So this iota is the identity. And then I also secretly have associativity phi, but I don't write it. So this composition is something in the endomorphism ring of x. And then I want this to be identity. And also there's something similar for the y. So these two are the conjugate equations. So for the case of compact group representations, so the meaning of this is clear. So what does it mean? If you had a unitary representation pi, then its contra-gradient representation is abstractly acting on the conjugate Hilbert space. So pi bar is acting on the complex linear space. And if you take an orthonormal basis in this finite dimensional Hilbert space, you can define these R1, R bar this way. So in that case, the 1 is just a trivial representation of complex numbers. So you just need to define the image of 1. And it's going to be something like this. So the standard embedding of trivial representation. And in the case of subfactors, you also basically do the same thing. But then, so the orthonormal basis needs to be replaced by something more elaborate. And for the case of compact quantum group, it's also very similar, but you need to take care of non-trivial isomorphism between some immediate algebraic construction and its unitarization. So anyhow, but this is the correct mental image to have it. And then, so once you know that R1 is this, you can check that this holds. So this equation is called the conjugate equation for x. And so in general, there are many solutions for this equation. So what you do is to look for the minimization problem for this R and R bar. Well, maybe I should just say like this. Standard if these have same norm in the first place, and also it's a it minimizes this product. So you can find it. It's just an algebraic solution in some finite dimensional space. Yeah, so assuming your category is semi-simple. So, and in this case, we call such a solution standard. And also the square of this, so something before taking the square root, so it's called the intrinsic dimension of x. Sorry? R and R bar. Yeah, inside here's bar. So, and so it's not obvious from this definition, but it's actually additive for the direct sum and multiplicative for tensor product. So. Okay. Yeah, so just another terminology. So we say C is rigid, C is the tensor category, if you can find this conjugate for any x. And we denote that you are as x bar. So it's unique up to unitary morphisms. And also, the important thing is that standard solution of conjugate equation is also unique up to unitary transformation. So it's our bar standard. Say T iota times R and iota T times R bar. Maybe so for the T unitary, this is just T. But another important thing is any other solution which does not need be standard, it's also like this, but with T just invertible.
Excuse me,
Yeah.
I thought rigid was usually used to mean that all those isomorphisms are actually equality on the nose. Like,
That's strict, I think. So there is another notion of strict tensor categories, where so you assume that the phi and all these were, yeah. Yeah, it's really confusing. So and also some people use different terminology, but yeah. So I think I'm following Voronovich's terminology here. Yeah. Okay. And another important thing is, so for rigid categories, so if the tensor unit is simple, so if the endomorphism of tensor unit was only scalars, then this category is automatically semi-simple. So C rigid and this endomorphism is scalar, then this is bounded by the square dimension. So because, yeah, so you'll see the ingredient later. So there's something called categorical trace, and that is faithful, and you get something like Pimson-Popper estimate giving you this. Okay. Oh, well, it's not data, so you just see it now. Sorry. So there is this thing called categorical choice. So let's say our x bar is a standard solution for x. Then you can define a trace on the Cx, this algebra, by this. So it's a normalized trace. Defined like this. So when you set T to identity also, then the result is going to be categorical intrinsic dimension of X. So you can normalize by that and get the user state, tracer state also. But the important thing is this is also equal to this. So you can instead use R bar to compute this. So this is called sphericity. So for the tensor category coming from subfactor, this is the up to normalization, this is the usual trace. And for the quantum group, you use invariant state, which might not need be trace for the B of H pi, but on the set of interdefiners, it is traceable. So that's what you should think about. And yeah, so this is the intrinsic categorical trace. Okay, so that's the more or less the general quick overview of tensor categories and its dimension theory. And what we care is the amenability in this setting. So amenability is about the sort of the combinatorial approximation of such C-star tensor, rigid C-star tensor category, and the question about how well such combinatorial approximation approximates the original data. So the combinatorial approximation is the fusion ring. So C rigid C star So I want to stay in this framework. And then, so we already,
You always assume finite dimensionality.
yeah, so this implies the finite dimensionality of morphism sets, but there could be infinitely many reducible classes. So that's what I allow. So it could be infinite depth subfactors or compact quantum groups with infinitely many representations. So at least, so this simplicity implies you can look at the reducible decompositions. So reducible classes makes sense. And I take representative. So that's one thing. And so you can look at the ring generated by this. So what does it mean? So you take the free commutative group generated by this set. But then, so you can decompose tensor product and define the ring structure. So what do I mean is this? So maybe US UT. So the product of two bases is P. So you look at the multiplicity of UP inside US times UT, which is given by the dimensional morphism sets. And so make it a multiplicity and add up this class of UPs. Then this is actually a finite sum, and you get a ring structure this way. And of course, using the reducible decomposition, you can also talk about the class of arbitrary object in C. So X, U, maybe MS, US. Is just a sum of classes. And also, the intrinsic dimension defines a ring homomorphism from this fusion ring into the real numbers. So X dx okay. So when we say a fusion ring, it means a ring like this and also homomorphism into reals, and then which should be positive on the generating set. So the But using this ring structure alone and without caring about this dimension function, we can also look at the regular representation of this discrete set. So each object small L2 of this set So how does it work? Call it gamma x, and then so it maps this basis to just x times s. So you just do the reducible decomposition of tensor product. So this is really the something which only depends on the fusion rule. And then, so there is an explicit bound. So this is always bounded by the dimension function. And in fact, so it doesn't have to be this intrinsic dimension, but it can be any other dimension function like that. So some ring homomorphism from the fusion ring, the Z on reducible C, which is positive on these generators. So and then, so we say that this category C is amenable if you have equality here instead of inequality. Amenable if so the examples are, for example, fusion categories when there are only finitely many reducible classes, or the what's called co-amenable Kac-Contan groups, or strongly amenable subfactors. Oh, sorry. There are only finitely many classes. And co-amenable Katz. That corresponds to things like compact groups themselves or amenable discrete groups, the dual of amenable discrete groups. And the known examples are things like the temporary leaf category for the parameter bigger than 2, and also the SU2 or SU2N contant groups. So SU22. Yeah, so that's a good question. So the dimension function is the quantum dimension representations. So yeah, you have some non-trivial positive operator coming from the square of antipode, and for these SU22 and SU2N, that's really something different from scalar. So you need to take into account of that, and yeah. So the dx is something strictly bigger. So what we want to do is to construct the formulation of Poisson boundary in the categorical terms, characterizing this amenability. Yeah, so, okay. So we want to define something looking like random walk. And first of all, to do random walk, we want to have the analog of L infinity functions on the discrete set. So yeah, I'm slightly changing from xy's to uv's, but yeah. So these are objects in C, and then so this is a family of natural transformations like this, eta. So x times u to x times v for all x, natural in x, and then also uniformly bounded. So each of these morphisms have norm, and they have to be uniformly bounded. So and if it was uniformly bounded, then we can call the supremum as the norm of this entire family also. So this is the analog of L infinity functions. And this naturality assumption means you can do the reducible decomposition here. So actually, you can prescribe this family just for the reducible, just determine the value at the reducible x, and you use the naturality assumption for the arbitrary ones. So characterize eta is characterized by eta s, which is eta s. So this is precisely what you need to determine, and this is something you can freely choose. I mean, as long as so these are morphisms in C. Okay. So we want to define random walk on this set. That's the precise goal. So to do it, we need to define the transition function. And the transition function looks like this, partial trace. So first of all, there is maybe I should go to normalized trace. So the fundamental thing is this. Oops. Something like concatenation of one leg. So if you had a morphism from x times u to x times v, then we want to concatenate the leg of x. So how do you do it? 1 over dimension star iota. You do something like this. And then this is a completely positive map if u and v are equal. And also, yeah, so if these were tensor units, then it is the normalized trace. But we can also sort of move the u and v free. That's the point. So transition map is acting on this C hat given by this px. So that's acting here. So to define the image, we need to define a family like this. So let's say we want to define the value at y, which is given by partial trace or partial trace of value of eta at x times y. Then this is well defined. So this is natural in y. And also this guy itself lives in C of x times y times u to x times y times v. And then we concatenate the leg of x. So the result is something in from y times u to y times v. And so yeah, if you want to identify the value, then what you do is to look at the tensor product. You reduce the decomposition of this x times y and use this. But of course, it's a highly non-trivial operation. So yeah, let's just leave it like this. Then the Markov operator is average sum of these transition maps for the reducible x's. So probability measure. Let's say mu is a probability measure on reducibles. Then the associated Markov operator acting on these C hat sets. Call it P mu. So that's the sum of mu P U S with the weight mu S. So each of these PUS are sort of completely positive maps. And this is just a probability measure. So if U and B are equal, then this is another completely positive map. Okay. So this is the Markov operator. And the harmonic elements, the analog of harmonic functions are just the things fixed by this Markov operator. Yeah, so this is, after you can define this Markov operator. This part is more or less straightforward. So we can talk about the subspace of mu harmonic elements now, mu harmonic families. And the surprising thing is, so they form a new category again. In other words, so you can define a composition of mu harmonic families. So let's say Xi, I should introduce a notation. So let's call the set of such mu harmonic elements PUV. But to be precise, it sort of depends on mu. So for the moment, this is still a suggestive notation that this is going to be a morphism set in some new category. So let's say Xi is in PUV and eta is in PVW. Then the first thing is this limit exists, eta times Xi, which should be limit in the maybe I should be a bit careful. PU Xi eta Xi. So this is just a composition in the C hat. So composition of these natural families. And then you start to apply this Markov operator many times. And then the first thing is this actually converges. So if you look at the value x, at the value at x, makes sense. So each of these terms is in CX U X V. So now we are assuming that this is a finite dimensional space. So the convergence, there's nothing difficult about the convergence in here. And another thing is this is associative. E tac psi is associative. So you can define a new category by saying that you start from the objects in original category C, and you say that the morphisms in the new category is this PUB, but the composition is given by this new product. And also another thing is, so this enlarged system contains original morphisms from U to B in C, because if you had the morphism like this, then you can just take sort of constant family like this, and then if this corresponds to a constant function, which is harmonic. So yeah, the origin system is naturally contained here. And then, so yeah, as Sunda said, so to be precise, you need to take the sub-object completion. So you regard projection in the new morphism set as the sub-object. And so in theory, you can get something larger. And sub-object. Okay, yeah, so I'm slightly running out of time. Sorry? Yeah? Yeah? Yeah, so C is always assumed to be rigid. Yeah, so I didn't really specify. But in order to make sense of things like this, C needs to be rigid. So I'm using standard solutions here. I mean, conjugate equation. Sorry? Yeah, it's not rigid then. Yeah, so yeah, sure. So, and also the unit has to be simple. Otherwise, the dimension is C star algebra valued, and yeah, it's a bit complicated. Yeah. Yeah. So, just to give you the idea, let me say what this corresponds to. For the contant group, this actually corresponds to non-commutative Poisson boundary in a bit indirect way. But for things like SU2N, I can tell you that this is the representation category of maximal torus. So this is n minus one dimensional torus sitting inside SU2N contant group. And yeah, so, oh, sorry, no, I mean this. Boundary is this. And this inclusion is just a restriction of representations. So here you get something strictly larger. This follows from Izumi Neshviev set. And also, so this construction in the subfactor case is the bimodule of standard model. And probably you'll see it tomorrow, the next time from the construction. There is another description, more so closer to the heart of subfactor theory. And yeah, so P n pi modules is NST pi modules.
What was that statement? I'm sorry, I missed the first statement.
Sorry?
That the non-commutative Poisson boundary.
Oh yeah, so okay, maybe so I'd say a bit in IITM talk. Sorry, yeah. So it's a bit complicated. So it's a bit indirect correspondence. So just take my word. It has to do with Poisson boundary, non-commutative Poisson boundary. Yeah. So the thing is, so when you think about the tensor functors from representation category quantum group, then so they correspond to particular actions of G, in fact. Sorry?
Effect of Q is disappearing in the Poisson boundary.
Q, yeah, sure. But then, so, yes, but Q has to be not equal to 1. So, yeah. But anyhow, so the thing is, this maximal torus is the maximal Katz subgroup of this SU2N. So, in a way, so this maximal Katz subgroup is constant. Okay, so let me just write the main theorem and show you some quick consequences. So suppose we also know that this unit in the Poisson boundary is irreducible. That corresponds to the random walk just on the reducible classes. The set of irreducible classes ergodic. So P mu, mu defines ergodic random walk. So this is the sort of classical shadow of Poisson boundary. Suppose this is classical shadow is ergodic, then so the inclusion induces functor. Oh, sorry. So I forgot to say that this P is also a monoidal category, C-star tensor category. So I'll explain the tensor structure later. So, so this inclusion this is a universal thing among the tensor functor into amenable categories, inducing this fusion norm as the dimension function is universal. D is amenable. And fusion norm is the dimension in image. So maybe I should say a bit more precise. So for example, this statement already includes that this Poisson boundary is amenable category. That's one thing. For example, you can, so in this example, you can see it. The Poisson boundary is just a representation category, usual group, so it is amenable. And also in this case, basically, yeah, so the standard model is amenable, so that's also part of Popper's theory. So I forgot to introduce the tensor product structure. So in order to define tensor product, you have to define these two operations, and then so the general thing is built out of this. So T is say in PUV, and W is another object. Then we want to make sense of these two. So tensor product from left and right at the level of morphisms. At the level of objects, it's the same. And this is simply the family like this. Dx times iota W for x. So this guy sits in Cx U W to x VW. So it's well defined in P U W VW. And the other one is a bit slightly tricky. So how do we do? T XW for x, and then so this thing is in CXW U XW B. So in total, this family defines something in PX, PW U W V. And then you just combine these two constructions and you can define the tensor product of morphisms. So this is how you define the tensor product. Okay, so I guess I'm running out of time. So let me just state the corollaries. So what can we say? Yeah, so for the case of quantum group, we have the classification of SUN type quantum groups. And so basically using this phenomenon and this universality statement. SUN type quantum group. So that's representation. So the fusion rule and the dimension function given by just the usual dimension of Hilbert spaces. This has the same data as SUN. And the most difficult part is to classify the functors from this category to Hilbert spaces, satisfying this condition. So essential part. So the image has the same dimension as the natural realization. That's the condition. But then this formula says precisely this. So now D is Hilbert spaces. So this is just the dimension of the image. And then, so we are saying the dimensional image has to be this, which is the amenable dimension function. And so by this universality statement, such F has to factor through this Poisson boundary, which is the representation category of torus. And that's really easy to classify. Because so this is, you just need to specify the compatibility of tensor product, which is by character on the Pontryagin linear of this. So it's some just skew symmetric matrices. So it's really easy to understand this. And in the subfactor context, what does it say? So it's when the P, this Poisson boundary is actually the same as original category. in this case, in the subfactor language, so as I told you, the Poisson boundary is the category of bimodule over the standard model. So, well, C is n bimodule, let's say, from inclusion n into M, and then C equals P is the same thing as these higher relative commutants of the tunnel stays the same when you take the standard model. So that's the sort of subfactor formulation of having Poisson boundary actually the same as original data. But then that's the same as amenability condition by this theorem. So then the principal graph, the norm has the minimal index. And the categorical dimension, intrinsic dimension is minimal index, in fact. So, so I think I can explain that the next time in the proof. So yeah, so by this theorem, so this corresponds to this, and so combining this, you get the equivalence of this condition and this condition.
Can you repeat this last part from the starting? When you were starting with the finite subfactor of n of n.
Yeah.
Then E is you are taking bimodule. Then what is P? P is the one your harmonic
Yeah, so P is the bimodules over standard model.
Not this, nothing to do with the P that you are defining so far. From E to you are creating out of E, you are creating a P, harmonic category, right?
Yeah, yeah. But then, so yeah,
This P is different.
yeah, it's the same P, and so mu is the sort of uniform measure on this M as n bimodule. So you can sort of look at this object, and there is a sort of uniform measure. So by looking at reducible decomposition, and you basically give the same weight. Maybe depending on the dimension, but there's a standard way to assign measure, and look at the random walk of that, you get this. Yeah, and so you see it in the proof. Actually, so there's another way to realize this Poisson boundary category as sort of more something like this higher relative commutant. So, but anyhow, so that more has to do with the proof of this theorem. So I'll do it the next time. Okay, thank you very much. So,